Thank you so much. Hello, everyone. Yeah, today I will give a talk about building best practices of building continual learning system. But I may have a mistake telling continuous learning instead of continual learning. But you will understand, everything is fine. So a few words about myself. I'm from Kharkiv, Ukraine. I work as a data science engineer at Quantum. So I've been engaged in several projects in computer vision, natural language processing, and reinforcement learning. But my main specifications and specialization is in computer vision, and I'm really keen on it. Also, as you see, I perform as a speaker and a mentor in different students' programs, internships, and other activities like that. And as soon as I'm professional, probably in computer vision, our talk will be mostly about continual learning system inside computer vision topic. Quick agenda about today's talk. So we will start in a quick dive into continual learning theory. After that, we'll define what tasks or tackles you will need to solve to build a good continual learning system. After that, we'll discuss possible solutions of that. Of course, all solutions is unique, so I will just tell you my experience and how we solve different solutions and probably practices of how to do that. And I will show you a practical example why it is interesting and good to build so complicated system, continual learning system. So continual learning is a fundamental thing probably in machine learning, and all the people think that, well, when something is AI, then you upload data, it learns somehow there, and after that, it always understands what you want from him, and I'm like this, but not usually like that. So continual learning system is a system which learns from new data, and to make your learning continual, you need to build the pipelines, a lot of code to make it really learn once in a while, once it is needed, and stuff like that. Yeah, so most teams that are tackling some problem, when starting an AI project, they come in to take all the data they have from the world, doesn't matter, label it, then train a model and serve the model through the platform or application to the users. After that, the user started to upload another images or other data into the platform, and the AI processes it, so you're gathering a lot of data, it's all unlabeled, and you have a lot of, in our case, images. And the idea is that you need your AI to be able to adapt to those images that you are sending to the system and make it reliable to work with any data you have. Yeah, and in the continual learning theory and in general design patterns of building machine learning systems, there is 4 stages described. The first one is a manual stage, so nothing really interesting. So you just take the data, train the model from scratch, get a new data, put it into labeling. Labeling is done, then you take in all this data and do it once in a while manually by hand. So it's not that interesting and very time consuming, unfortunately. Then you become a little bit clever, and you do a periodic run of this. So you implement some code to run it as separate services, or a single service, it depends on your architecture, and run it once in a while. You have some amount of data new available, you put in for labeling, labeling is done, okay, run it. But it's still not really efficient. And here we come with 2 problems even in this stage. So you need to automatically define which model is better, a new one that you trained, or a champion one, which is currently in production. And it's really hard usually to do it automatically, because when you're analyzing, for example, deep learning, deep neural networks, it's a lot of metrics, and you try to go between them and understand which metric is more relevant in our case, in each case specifically. And the second topic is that training model from scratch is really time consuming, and in this case, if you're using cloud platforms, it's also money consuming. That's why it's much easier to make some sort of stateful training instead of stateless training, and only fine-tune your current production model on a new data. But in this case, you will need to do a versioning. It's another task that you will need to solve. And yeah. So yeah, and here we come to the third stage. So it's automated stateful training. The idea is the same as in stateless one, but we are just fine-tuning, and it becomes less time than less money, and you can do iterations faster and more efficient. And this fourth and the final stage is a continual learning, like in this ideal way. So it is another like huge sample of code or like service implemented there. It is called trigger on this slide, but it's not actually just a trigger of the pipeline. So it's some sort of analytic service which checks if you have any changes as data or your model is degraded in performance, or even create some sort of sampling method for new data which is like more relevant to fine-tuning the model. And it is probably the hardest part there. So what tasks we will need to solve? So to define like what can we do with a trigger. After that, I will tell you about the possible platforms that you can use. The same for data labeling. We will define like why do we need version control and how it works, and how challenger and champion model comparison should be done, and like what is the best way to do that. So first about trigger. Here is 4 possible options how we can run a trigger. So first 2 are pretty simple. Time-based is completely simple. So you run your pipeline once in a while, like once a day, it doesn't matter. And volume-based, it's mostly for projects that have non-uniform getting of data. So like we have data once in a day, and when we understand not once in a day, like non-uniform in general. And when you understand that your data is like increases 5%, for example, so then you run a pipeline. Third and fourth method are more complicated. The first one is performance-based, so you need to understand if really your model performance degraded through time or through new data. But the problem of this method is that it could be forget this word. Okay, like. It could be too late to update your model when your performance really degraded and you provided some bad solution for your customers in this case. Drift-based is more complicated, but probably more efficient one, because you detect the drift in data coming to your platform, and you can understand, like, do you need to run training on this specific data, and the iterations could be in more precise time and in more needed time for producing good value for your customers. We will discuss mostly data drift part. Data drift is generally when some distribution on any stage of your production model inference happens. So it could be a concept drift, feature drift. Also, there is a lot of types of drifts, and all of them could be eliminated in the best way. But usually, the general idea is the data is drifting somewhere due to some reasons, probably just the camera of these images changes, or the distribution of classes in the road changed, and you need to eliminate that. So I want to present these guys. They call deep checks. They didn't pay me anything for this advertisement of them, but they did really huge product. It's an open source one, which helps you to detect drift. Of course, it's not necessary to use some sort of platforms. Sometimes it's really possible to do to detect all data drifts in a manual way, in some handwritten code and other stuff. But they work really fine for a lot of tasks that we checked. So they create some sort of HTML file as well as API. So as you see here, so you can have pass test, didn't pass test, and you can check if your model is performing good. So you can set the threshold there and understand how your model is performing. So it's a general framework for checking the performance of the model. As a result, there you're getting a lot of different checks, including different types of drifts, class performance, and other interesting metrics that could be useful for you. And producing in that HTML file, you have even parameters specifically for each image, what part of image or what characteristic of image changes. So as you see here, we have a RMS contrast drift, and here is a brightness drift, and it's really detectable, but the drift is not that good, that great to be considered as a crucial one. The problem in their case is that they only implemented for PyTorch for now. Probably they will extend to TensorFlow, but with some manipulations, it's possible to make it able to work with TensorFlow as well. Yeah. So we now know how to detect drift. Of course, like it's not a universal solution, but anyway. About the platform. So probably just one guy coming to the conference and saying, well, Google Cloud is the best one, like will not be a case for you to change your cloud platform. But here is a, like, we define two major features for the platform we are using. So it should be ML oriented. So you speak with the documentation of that platform like on the same language. Also, like we assume that it is a good case when it is cloud native. So it has a good integration with all the services like SQL servers, just the storage and everything. So like huge providers like Amazon, Google, and Microsoft are really good in this case. Also, we had a really great experience with Kubeflow, and the case of it's not cloud native, but it is possible to run your pipeline on different stages on different clouds, and it's really useful. And also, I will talk about that later, but Kubeflow model serving is really good, and it's really like easy to use. Yeah, we are currently working mainly on Google Vertex AI, and as you see, you can get like with not much Python code, you can create a simple pipeline. But this was not simple, but all the services are separated, and you understand what you're running after on each step. And here is a pipeline of how to train the model from the very beginning till the deployment, and some analytics for future runs. Yeah, so we know how to run the pipelines on the platform, so we need labeling. Probably any team coming to the AI platform thought about like we'll create a labeling tool by ourselves. It will be on our local machine, it will be completely for us, but like it's not the case. We tried that a lot of times, to be honest, and we understood that cloud-based, probably even for money, it's much better than any handwritten solution. Cloud-based it should be because like when you're getting bigger and expanding, so you have more than one annotator, for example, you need to manage all the data sets and more than one task. You need to manage data sets and be able not to label each image twice, or not even image, like doesn't matter. So you can be able to create labeling tasks for each annotator and like for some part of image. Also, it's really important when that data labeling to perform consistency tests if you have more than one annotator, because consistency tests sometimes, and they could be automatic also inside the pipeline. It's really important because like it happens once in a while when you understand that your labelers are doing completely the different job and they understand the idea completely different, and it's really like influences the performance of the models. Also, the main thing, like in context of continuous learning pipeline, is that you need an API, because it should be easy for you, like when everything is running automatically, it should be easy for you to access the data which was labeled and to publish new data available to the labeling platform. Yeah, so here is a few examples of labeling platform for now. Well, I checked the internet and like it's much more than I presented here. So we are currently working with Dataloop, and I think that we are a bit stuck with that, because all new ratings of 2023 saying that SuperAnnotate and V7 are much better than Dataloop. But like in our case, we are a bit stuck with that. Also, Label Studio is an open source solution, so you don't need to pay anything for that. It's usually a good option for like small teams and small projects just starting. Okay, so we can collect data, we can label it. Then we need to find how to store the data set. So these tasks, I can tell you only about like the image format, computer vision. We tried different ways of storing the data. Zip archives are pretty good, but because like it's fast upload and download if you have a lot of data and it's stored on the cloud, so like it's not possible usually to put it on the one machine. So, and usually upload and download is really simple, but when you try to debug something, you're unable to take a part of it. So for this case, it's not that good. TF records are also pretty good way of storing data, because like all the metadata, label, and other needed parameters could be stored inside the TF record. And also they support like pretty quick getting reading and writing data to the cloud. But like as usual with not image format, it's hard to inspect them, and Sometimes it happens with that you cannot integrate TF records inside the PyTorch pipeline. So like in this case, it could be a problem. Images are always good, but you always need a special file with all the labels and metadata. And like it's hard to manage it because like if it is stored all together on the cloud, for example, you have a separate for example, metadata file, and you need just to take part, you need to get that metadata file, take only those you need, then copy all that passes, and like sometimes it's really complicated. Also, we found a pretty good solution. It's called Web Dataset. It's also an open source solution. The pro with that, you can easily run your first demo test with it. So it's easy to set up and to run like the first run. But after you try to integrate it inside the pipeline and make more complicated stuff with it, the problem is that documentation is mostly just the source code. So it's impossible just to read like a few words and understand what it is doing. But like source code is, for someone, it's pretty good. Also, it's not yet implemented for all types of PyTorch datasets. So it's currently supported, as I remember, just the iterable one. So for other types, it could be problematic to run it. Yeah. After that, we are coming to the model serving. You have a trained model, and you know its performance, and you understand how fast it should be run. Then you decide, like, do you need to convert this model into some format, or you can leave it just PyTorch, TensorFlow, or I'm not sure if anybody using other frameworks. So in this case, there's like two options. You can create your own container with all the inference, like pre-processing and post-processing you need, or you can use serving platforms. In case of serving platforms, nearly all the platforms support some sort of serving. And it's usually much faster than implementing your own code, deploying it somewhere. But in most cases, if you have some like complicated pre-processing or post-processing, like my personal recommendation is recommendation of my team that you should definitely write your own, because deploying 3 times like for pre-processing, serving itself, and post-processing is really hard to do. Like we are not DevOps engineers, then like it's not easy for us. Also, in case of using serving platforms, that you can use one code for inference and test, so you can always may have errors like comparing them too. But like speed is, if you need a runtime performance, then like it's the only options. Like personally, I really enjoy Triton Server by NVIDIA, and it's like, as I remember, 36 times faster, and it's really true. Okay, we're coming to the last stage of the pipeline. How to define how to find if your new model is better than the previous one, as it is set on this schema. So you take a champion model, like create a replica of it, update it with new data. You have a challenger model, and comparing them. For comparing them, it's like key principles probably. That it should be business-based, because unfortunately, classical metrics from deep learning and machine learning are not that good for all the tasks. So they cannot like produce the real value to the customer. Then your metric should be business-based, and it should be used mostly for like in these pipelines. About high coverage of all cases, like anyway, if you even have a good business-based metric, you should not forget about like classical machine learning metrics. Because like without them, you won't be able to, on many iterations, understand like where your model is going when you're trying to analyze them. And like it's more an option than the principle. Like it's great when you can use this metric as a base metric for sampling data on future iterations. So for example, well, I will show you an example how we did that, and you will understand what I'm talking about. So here is a task made by us. We get the data of images from drone of the trees on the field. And the idea, like the task is to segment those trees and find each tree specifically. So the first stage of our algorithm was to create a U-Net architecture network and get a segmentation mask of the trees. And as you see, like it works pretty good. And after that, you need to separate each tree. And here is when all the metrics are failing when we're talking about intersection over union or others, so we need to create some sort of some difference. So for this case, for the first stage, we used intersection over union, like a classical metric for segmentation. And also we developed a completely new specific model. It was a classification model for each polygon. It's based on shape. And it checks if the polygon is correct or not. And it was like a great solution because it works like for a lot of time now, and like it's producing pretty good results. For about testing, here is a point which is really important, that you need to check the performance both on the labeled dataset that you had previously accumulated like over iterations, and a new label test separately, because combining them all together will make you a bit confused about the results, and like your continuous learning decision-making system a bit confused. So like the main idea is completely simple. So on iterations n+1, you just need to mix and sample all the data you had on the previous stage and add new labeled data. And it could be like a perfect test. And when comparing them, you can like you can make some decrease in performance on your iteration n data, because like you're going into future, you don't need really to understand like what was 2 years ago and other stuff like that, but you need to be completely sure that on the new data available and new data getting to the system, you are performing much better than your previous model. Here is a pipeline for the task I described to you with polyorganization. So it's a bit more complicated than the previous one. It has like a normal training pipeline. After that, it is mostly for decision making. So you need to perform all the steps on different data sets and check them, and then deploy the model. And as a result for it, you can see that training time for like retraining one iteration of the model took 1 week previously, because like I did everything manually, just needed to collect data, wait for it to be collected, then sample it and other stuff like that, train the model. And currently it's just working for 1 day, like a little bit more than 1 day, but completely automatically. So my working hours were 40 hours and just 1 hour just to make a cup of coffee, check my email, that everything went fine, and we get a good new model in production. And I forgot about like the metric. In this case, let me go back a little bit. So after we get like the results for each specific tree, if it is a good shape or not, we can create some sort of pass rate for each image. And after that, images with lower pass rate are going into future training, and that's how we improve the performance of our model. So it's like a core metric for us to sample data for labeling and retraining future models. This is mainly it from my side. So continual learning won't replace you. Anyway, you will need at least 2 weeks to implement all the services and make it run fluently and okay. So like implemented without fear, it will really help, and you will enjoy doing like getting the results from it. My name is Mykyta. I work as a data scientist at Quantum. Feel free to reach me. It's not me, it's company, but like you can find it somewhere. Me somewhere there. So thank you for your attention. I'd be glad to answer your questions.
That's right. Hi. My question is, how much more does it cost to continually update a big model compared to a small model? Is the cost proportional, or maybe is it easier in a big model?
Well, it usually takes more time to train a big model. Like as usual, so the cost of computing cost is much more for bigger model. But like when we're doing continual learning pipeline, it may take less, like comparing to manual small model. Like you understand what I mean? Mm-hmm. Because like our working time is still money, So like comparing to that, like you can create a bigger model and in continual learning pipeline, and it will be like much cost efficiently than like in the vice versa case.
Okay, thank you.
Okay. Are there any other questions? Yes. Okay.
So you talked about the stateful training model.
Yeah.
And I'm wondering if you train, you got the new data set, right? You train your model and the champion model performs worse than the current one that you are using.
Yeah.
So you're not switching to the champion one.
Mm-hmm.
So what happens to this new data set?
It is stored. Like in our case, and as we implementing it, so when you get a new model worse than the previous one, so we get an email, so an alarm to all the participants of that pipeline. So like something went bad. And some iterations may be like that. So if the decrease in performance is not that big, we are just not deploying, and we are storing this data. If something goes wrong, so it's still stored and updated in future trainings, like took into future trainings. And if you understand that like the improvement has stopped, so we go there and analyze what is like wrong with that data and why like it is not possible to update the model anymore. So it's still manual work. It's why it cannot replace you at all.
Okay, so you just store the data and add it to the
Yeah.
next batches. Okay,
Yeah.
thank you.
Hello, I just want to ask you one question. What kind of images did you use for tree separation? Was it just RGB or multispectral?
We used just RGB images.
Okay, thank you.
Okay. Are there any questions? I don't see. So thank you very much for your participation. Mykyta, thank you very much for your presentation.